Namaskar. I am Naresh Chandrapant, a professor in Department of Geology, University of Delhi. Today, we are going to talk about a very common and humble mineral, quartz. It is a very special mineral in many ways. As you know, minerals constitute rock, but quartz is little different from other minerals, that it represents one of the rare pure phase, which means that its composition is fixed, unlike most other minerals which have highly variable composition. Quartz is essentially made up of silicon and oxygen, and there are hardly any other substitutions on these cation and anion. Quartz represent one of the most important and commonly occurring mineral on the surface of earth. As you know, the silicates are essentially classified in terms of a basic building unit, which is known as silicon tetrahedra or SiO4, expressed as SiO4. There are various arrangement of SiO4 tetrahedra, essentially in 6 different types, which lead to different types of silicate. Quartz represents a class amongst these, which is known as Tektosilicates or otherwise called as framework silicates. The studies on silicon tetrahedra have indicated that the silicon to oxygen bond length on an average is about 1.62 angstrom. If one of the oxygen bridges the tetrahedra with other cations or with other tetrahedra, the oxygen diameter changes by about 0.025 angstrom in comparison to the non-bridging oxygen. So, therefore, the presence of other cations and anions affect the bond length between silicon and oxygen. Similarly, the bond angle between silicon and oxygen varies from 120 to 160 degrees. On an average, in an unstrained silicon oxygen bond, it is around 140 degree. The variations of the bond angle and bond length lead to various structural variations, leads to different kind of symmetries, and leads to different polymorphs of quartz or SiO2. If we look at the quartz as a mineral which occurs on the surface of earth, that mineral is known as quartz, but if we heat this at a temperature of 857 degrees centigrade, it transforms to another polymorph of quartz which is known as Tridymite. With further heating, it transforms to a polymorph known as Tishowite, and at 1700 plus degrees centigrade or 1713 degrees centigrade, quartz finally melts. At high temperature, the deep crustal depth and at mantle depths, quartz occurs as a mineral which is known as coicide. We will see what are the structural differences between these. The presence of these polymorphs or these forms of quartz can be seen in a pressure temperature diagram in this figure. In this diagram, the vertical axis represents pressure in kilobars and the horizontal axis represents temperature in degrees centigrade. As you can see, at lower temperature and lower pressure, the variety of quartz which is stable is known as low quartz. At higher temperature, it is called as high quartz. If you look at close to the horizontal axis at temperature at over 857 degrees centigrade, the high quartz transforms into Tridymite, and at further at 1470 degrees centigrade it transforms to Crystallite. The Crystallite melts at 1713 degrees centigrade into liquid, which is the melting point of quartz. If you look at the upper part of this picture, the form of quartz or SiO2 which is stable is known as coicide. We will look at the structural difference between the coicide and the quartz subsequently. Let me draw a typical SiO4 tetrahedra for you. Now, in this tetrahedra, all the four corners are occupied by oxygen. In between these oxygen, there is a tiny silicon which is present. In framework silicates, the corner oxygens are all shared. So, this oxygen is shared, this oxygen is shared, this oxygen is shared, and this oxygen is also shared. This leads to, in this, the formula is SiO4. The sharing of these oxygens leads to the Si:0 ratio as SiO2, and this is the formula of quartz. Now, presence of, as I mentioned, other cations around it changes the bond length between oxygen and silicon. If all bond lengths are equal, they will lead to a particular kind of structure, but if on one side one bond length is distorted, the structure will be of a lower symmetry. Therefore, presence of other cations control the structure of silicate minerals. In case of quartz, there are no significant substitutions. As I mentioned, it is a pure phase. Therefore, the effect on the bond length is dominantly on temperature and pressure. When we talk about the transformations in quartz from low quartz to high quartz to Tridymite, Crystallite and coicide, there are two kinds of transformations which occur. One where there are significant changes, like for example from quartz to coicide. There the normal silicon in four-fold coordination changes to a rutile structure, and that kind of transformation is a reconstructive type of transformation. Whereas when there is a small structural change by bond length, that kind of transformation is known as displacive transformation. To understand this, we have to look at the structure of quartz. The basic building unit or basic structure of quartz is in form of a three-fold helices or spire parallel to C axis. So, consider this as C axis, and you have a tetrahedra here, then a tetrahedra which is facing on the other direction, then a tetrahedra which is facing in other direction. So, it acts, it is almost like, because of the different facing of the apices of the tetrahedra, it is like a screw, and since screw can be rotated in clockwise or anti-clockwise directions, so the basic unit of the spire produces two kinds of quartz which are called as left-handed and right-handed quartz. This reflects differently in crystals, and we can see this in the figure which I am showing you now. We can understand this by this diagram, where there are left-handed and right-handed quartz reflecting the spiral structure produced by a typical arrangement parallel to C axis is shown. In this diagram, this represents the C axis in these two prismatic crystals. Their faces are named as M here, Z. Now, if you look at the left-handed quartz, the arrangement of M is a mirror image of arrangement of M on the right hand side quartz with respect to the left hand side quartz. The same is true for the face Z on the left hand side quartz or left quartz with relation to the right hand quartz. And similarly, this is also reflected in the faces labeled as R in the lower part of this figure. So, this typically represents a enantiomorph type of structure which is common in quartz. One also sees a difference that there is a lack of center of symmetry in quartz, which means that one end of C axis is not represented similarly on the other side. So, that leads to certain specific properties which are associated with quartz, and these are known, this is known as piezo electricity. This particular structure of quartz is useful in quartz atomic clocks also. The C axis of quartz is longer than the A axis, and as usual the two horizontal axes are equal. The ratio between the two being 1.10013 is to 1. 1.10013 represents the C axis and 1 represents, in terms of ratio, the A axis. The absolute length of the two axes are 0.4915 nanometer or 4.9133 angstrom for A axis and 0.54051 nanometer or 5.405 angstrom for the C axis. When quartz is examined under thin sections, it displays a first order gray or sometimes yellow color, interference color. It has a birefringence which is low, therefore, it also has a Ri which is close to that of glass. So, it shows a very low relief in comparison to the glass in which normally the thin sections are made. So, lower birefringence and first order interference colors typically identify quartz. However, in comparison to other such minerals, it displays no cleavage, it has no cleavage, as well as it often displays accumulated strain as wavy extinction. So, therefore, the entire grain in strained situations or strained grains does not becomes extinct when the stage is rotated under cross polar. That is a distinctive property along with the lack of cleavage for identification of quartz under microscope. Quartz occurs in almost all types of rocks other than the ultramafic magmatic rocks. It generally occurs as anhedral crystals. However, in volcanic rocks, and which can be identified typically by the euhedral nature of quartz, in volcanic acid rocks it often occurs in euhedral form. There are many forms of quartz. The low quartz normally has trigonal symmetry, but there are many ways in which SiO2 occurs as polymorph. We will be discussing some of these types now. So, opal is a mineraloid form of SiO2. Normally, it has some amount of water. So, there is the formula of opal is SiO2 with some amount of water. It occurs as cryptocrystalline minerals and is generally redeposited form of SiO2 dissolved by several natural processes. it occurs in near surface situations and near surface processes. Tridymite normally occurs in wugs and vesicles of volcanic rocks, something like rhyolite, andesite, dacites, etc. It has a structure which is of AB repeat type, where the B layer above A layer results from an inversion. So, there is a symmetry which is associated with this. It is parallel to 001 surface, and at about 117 degree centigrade the inversion occurs. So, tridymite represents a particular, normally a particular kind of association. Cristobalite generally occurs as enantiomorphs. It has pseudo isometric structure below 230 degree centigrade. Above 230 degree centigrade it has isometric structure. The stacking of layers in cristobalite is ABC, ABC, unlike that of tridymite where it is AB, AB inverted, and the structure in the above 117 degree centigrade in tridymite is hexagonal, whereas above 230 degree centigrade in cristobalite it is isometric. So, that is the major difference between the two. The Coicide polymorph, which is very special, a high temperature form, is monoclinic. The beta angle in coicide is 120 degrees, and on surface it normally occurs as very tiny inclusions within diamond, garnet, zircon, etc. Because on surface, if it is present in matrix, it does not survive as coicide, it transforms to the lower pressure forms. Coicide allows us to infer the deep processes. For example, in many of the diamondiferous kimberlites and eclogites, the presence of coicide has suggested pressures of more than 27 kilobar for that particular rock or mineral. Stishovite, the last form of SiO2, is a very rare form on surface of earth. It is only reported from an impact, meteorite impact crater in Arizona. It can only form on the surface of earth by a meteoritic impact, otherwise it is not reported from normal terrestrial rocks at all. We will look at the tridymite cristobalite transformations very interestingly in these figures. The two figures represent two different situations. In the first, the tridymite is the host, within which part there is a cristobalite transformation. If you look at this image closely, you will see that the line marking 001 represents the 001 plane of tridymite, whereas along 111 plane of cristobalite there is a twin like situation which is coming. So, therefore, if this transformation is seen or recorded in a mineral where this transformation has taken place with tridymite as host, there are likelihood of twin like lamellae of tridymite and cristobalite with the planes parallel to 001 for tridymite and 111 for cristobalite. If you look at the structure, the tridymite structure is typically AB, whereas when it transforms to cristobalite, it is ABC layers which are present in the cristobalite structure. So, this is a parallel arrangement along two crystallographic orientations, but when cristobalite is the host and there is a transformation to tridymite, four different orientations can be possible. As you see in this figure, the four different orientations are represented by 100 of Tridymite, 001 of Tridymite, 001 parallel of Tridymite and 001 at an angle with Tridymite. And these are represented in this figure on the right hand side by the orientation of 111 plane of cristobalite. So, therefore, depending upon in which direction the transition has taken place and which is the host, one expects different structure seen in the mineral SiO2. So, today we have learned that the silicate minerals constitute bulk of the surface minerals which are seen. Quartz is one of the rare pure phase which is present naturally, and there are various polymorphs of quartz which represent or function of pressure and temperature conditions which they experience in different parts of the earth's crust and depth. Thank you.